And our speaker today, it's my pleasure to say, is Vince Matsko. Vince is a retired math professor, and as retired math professors tend to do, he's getting into various other kinds of mischief, much of which involves writing. In fact, he's right now taking a break from a writing workshop in Florida. He's already written a number of things, and the relevant part of that is that includes books about puzzles. And I will be sharing some links to Vince's writings in the chat after he gets started, and to his webpage, which have a lot of very amusing things.
All right, I just want to say thank you all for being here today. I was very happy to be invited to give a talk for Celebration of Mind. What I'm talking about today, I'm calling algorithmic puzzle design, meaning using code. Mathematica is my program of choice in order to design puzzles. And basically what I am going to do is look at several ways which I do that. Here's a picture of the volume 1, and the links are going to be in the video. I'm sorry, in the chat. This came about actually as a result of the pandemic. I was moving to St. Petersburg. I didn't know anyone. I was stuck home alone for so much of the time. And the idea came to me to write a puzzle book, and not just any puzzle book, because I had grown up with puzzle books all my life, but trying to find new spins on things, trying to find something different to do. And the genesis then of the book was exactly that. There's a lot of different kinds of puzzles in the book, and people ask me, well, how do you come up with so many different puzzles? And yes, it means you have to be a bit creative, but I let Mathematica do all the heavy lifting for me. This book could not have been written without very intense use of coding. And that's why I was able to publish 2 books in 18 months, which takes a bit of work in and of itself. But what I did for this talk is I literally went to every folder I had in my folders of these books and looked at all the Mathematica code and looked at the ways in which I use coding to help me with my puzzle design and creation. And the 6 ways I found in kind of simplified the number of them, but simple predicates, complex predicates, simple searches, complex searches, interactive searches, and layout. And what I'm going to do is just go through examples of each one of these to give you an idea how I use that. Now, I know some of you are coding experts, some of you are amateurs, and some of you don't code. So I've tried to make sure things are as transparent as possible. And those of you that use Mathematica will be very familiar with a lot of the syntax that you see. So let's just start off with the pop quiz. Think of a word of at least 11 letters such that all the letters in the word are different. 30 seconds. You cannot use uncopyrightable since that's a well-known word of that sort, but see if you can just think of one in the next 30 seconds. Okay, so did you come up with all 168, I guess is the question, in 30 seconds? And well, we got one. Evan said someone did copyrightable, which is kind of cheating since I gave you uncopyrightable.
That was Arthur, but Larry Washington has said facetious.
Facetious, you'd have to say facetiously, wouldn't you?
Yeah, I guess he must have meant facetious.
Because facetious only has 9 letters.
Yeah.
Okay, so Mathematica has a 75,000 word dictionary, and the average person knows, say, 20 to 35,000 words. But what I did here is, in less than 1/10 of a second, you can write a simple search which finds 138 11-letter words, 27 12-letter words, and 3 13-letter words, which have all the letters different. Now, there are 494 10-letter words like this, but I was looking, curating that list, and I found countryside goldfinches and dragonflies. And since there's 11 letters, I thought of using the British custom of 11s, which is tea around 11 in the morning. And I'm just going to read you excerpts from the actual puzzle just so you see what's going on. So Morris was visiting his great friend Clive in the English countryside one sunny weekend. There was a light breeze blowing. The day was unusually fine. Fauna were in abundance. Morris spotted a tree sparrow, and Clive pointed out a pair of goldfinches. Morris commented upon the butterflies flitting about, while Clive was intrigued by the precision flying of dragonflies on the hunt for gnats and mosquitoes. And then further down in the puzzle, now Morris, what an interesting word juxtaposing. Really, Clive? Just an ordinary sort of word. No, seriously, 11 letters, all different. Surely it can't happen all that often. Well, perhaps some clever chap will do a puzzle where you fill in words with 11 different letters, but as I'm rather peckish, I could really care less. And the point I want to make just in reading this and showing you this is there is no way I would have ever tackled a puzzle like this without the help of mathematical or some technology. My command of vocabulary to be able to come up with words like that is just not good enough to do that. And so this is a kind of a puzzle which I think you can't write, or I shouldn't say it's not possible to write, but I can't write it without the use of technology. I just made up a silly acronym, but I call this a Porto. It's a puzzle otherwise relegated to obscurity, meaning without some sort of technological help, there's no way that I would have been able to create a puzzle like this. And this is the first example of the 6 simple predicate. And if you haven't done much programming, you know that there's a data type called a string, and words are usually stored as strings of characters. And you can see how simple it is to find these things using Mathematica. You have a predicate that says if W is my word, the string length is the number of characters in the word, so that's 11. And let's just unpack that second line. If I've got a word, characters gives me all the individual letters in that word. What the union does is it will eliminate all duplicates because you want all the letters to be different. And then if you still have 11 letters, that means you've got 11 different letters. And you do need to check if the string length is 11 because maybe there's a 13-letter word that has 11 different letters and you want to avoid those. And that search took less than 1/10 of a second. So already we've got this list of words that can be used to for this particular puzzle. So that's just a simple example of using technology. Now let's go to a complex predicate. So this is a puzzle from the first volume of the Puzzle Cabaret called Stairs. And as you can see, the CAR letters look like they're parts of stair steps. And the idea is you have to find words with CAR in the various different positions and, using the clues, fill in the words. Now, the interesting thing is here, of course, the clues are not in order. They're alphabetical by the clue definition. So coconutty cookies would be macaroons. And you can go on and take a look at all the other ones. But again, this is an example of a search, and it's a bit more complex, not super complex, but there's a very nice command in Mathematica called string take. So if I have a word and string take with the word and the numbers 1 and 3, will extract the first 3 characters of the word. I want to see if car, those words that have car as the first 3 letters. And then if I string take from characters 2 to 4, then I have all the words that have car from in the 2nd, 3rd, and 4th positions. And then if none of them are empty, because we need to have a clue for every word, then we print them out. Again, takes Mathematica less than 1/10 of a second to spit these out. Now, by curate, what I mean is, let's take a look at what the output from stairs with car and 9 gives you. This car works. Luckily, streetcar, which is the one where the car is at the end, is a accessible word. Of course, car at the beginning, there's so many choices, not a problem. If we look at the row starting with baccarat, barcarolle, it's a musical term. It's not so, or not so common. Peccaries are, of course, these little pigs running around the forest. Placarded, usually placard, we don't see it as a verb, but discarded, I liked. And that was the clue for, if we see back here, tossed out would be discarded. So I need to be able to find an accessible word in each of those lists. I think readers who found out that the correct answer was urticaria would probably be a little miffed. How on earth would someone come up with urticaria or metacarpi? So I do want to make it challenging, but I still do want to make it accessible, obviously. So there's a lot of this curating going along because Mathematica can find all these things, but you have to actually be able to make a puzzle out of it. And we'll be talking about that idea later on. Okay, here's another example. Now this is going to be an example of a search. And I call this puzzle unique triples. And if you know a word that fits in the blanks of any of these, if you want to put them in the chat, Evans will give a shout out to you and the word if you want to think about it while I'm speaking. But the word CUU occurs in vacuum, and of course vacuums, vacuumed, vacuuming, but essentially in one word. Now, those of you who are puzzle designers and writers, and I know many of you are, uniqueness is really important, at least for me. But how do you find out if there's only one word? Now, I should point out, Evan said, someone said punch kit, which I do not know what a punch kit is, and it's not in my Mathematica dictionary. The one I have for that is latchkey, but that is an important point. When you start doing things like this, you'll find out that everybody has their own dictionary. I've even looked at the New York Times. People have curated lists of words and clues for writing crossword puzzles, that it really does depend upon your dictionary. And I may at some point try to enlarge it, but if I want to search within a dictionary, you do have that constraint, is you're stuck with what you can find in your dictionary. But in any case, it's very easy to find these relative to the dictionary. Many of you are familiar with the term regular expression. So in Mathematica, there's a string match command, which checks if a string matches a particular regular expression. So if I have AAR and I put asterisks on either side, it's looking for words that have AAR anywhere within them. And you get the 4 there: bizarre, bizarres, aardvark, aardvarks. There is an aardwolf, if those of you that know something about animals, but it's not really as commonly known as an aardvark. But we only have about 18,000 combinations to check. But again, since we have Mathematica, we just let it do the heavy lifting, and you get about 1,500 of those. And we'll take a look at that in a second. But the point is, this is just a very simple search. I select from my word list all the things that have an AAR in them. And, again, it'd be really hard to find all of them on your own. And that's why we use encoding. So here's what I do. I export it to this. You can export it in CVS format and then open it in OpenOffice. And again, there's not a lot here that you can use, which is why it's nice that there's 1,500 lines. Am I going to want to use BOD for AAE? No, that's not a really interesting word. Am I going to want to use, let's look at AFN. I do have AFN there. And I do export, by the way, things that have 6 words or fewer, because we have to allow for conjugating the words in plurals, etc. But when I see deafness and hafnium, I'm pretty okay with deafness. I had to Google what the mineral hafnium was. I don't think that's something in people's common parlance. So using deafness for AFN, I think works. I do try to do things like I would avoid Aegis because it starts with AEG. I think that's a little perhaps sometimes too obvious. But crabgrass, ABG, that would be, I think, a good one. It's a commonly known word, and there's really only 2 things: crabgrass, and it's plural. So, but you can see that if I wanted to write another puzzle book, which I'm almost done with volume 3, hopefully be out this semester, you can see I can have a unique triples puzzle in dozens of books to follow. And that's really one of the points in creating puzzles like this, is it makes subsequent volumes easier to write. But true to my mission, I always feel like every book is going to have about a dozen new puzzles that aren't in the books before, because I feel like if my whole point here is in creating new puzzles, then I need to be true to my mission, and I can't rest on my laurels. I still have to do work in creating new puzzles. Now we're going to get into a more complicated search. So that was a simple search, which was just a few lines of code. So I'm going to talk through this type of puzzle I call a pentagrid. And for those of you who know me, you might know that I'm a huge fan of polyominoes. I've given workshops at the Museum of Math on polyominoes. I've done summer workshops for kids at various different places. And my website design is hexominoes. It used to be pentominoes, but I just think they're cool, very cool. And what I've got are these grids divided into pentominoes. And if you look at it, you've got the words bingo, acted, conic, heats, and polar. But also, if you read left to right and top to bottom, you've got the words bacon, ingot, edict, cheap, and solar. So you're having words that go across and also within the pentominoes. Again, am I going to want to sit down and work these out? No, I want to be able to use Mathematica. Now here is the actual puzzle from the book. That was just a sample. And these puzzles with the 12 pentominoes and a 2x2 square fitting into an 8x8 square. There's, websites that just have lists of all of these. And so, you first start by looking at your grid and looking at line 1. Now, the piece clues, again, are not in order. They're in alphabetical order by the definition, but the across clues are actually the clues. And number 1, the answer is starched, as you might guess. So let's just take a look at what the process is. I can use Mathematica to search, look for an 8-letter word such that the first 4 letters begin some 5-letter word. The 5th and 6th letters begin some 5-letter word, and the last 2 letters begin some 5-letter word. So many 5-letter words contain CH at the beginning and start with ED, and you could think of several for star right off the top of your head. So then we go to the next one, and we can pick out spillage because stars, is a 5-letter word. The P, we don't need to check the P because any letter could be the beginning of a 5-letter word. Now we've got chill from the ILL in spillage. You've got the A, and then I could do edges, edged, edger. There's ways that you can put a suffix on EDGE, and then we can go on to the next one. Now, here's the problem: is the search space as such is too large. I couldn't get efficient algorithm to work. There's 12,000 8-letter words approximately in Mathematica's dictionary and 5,000 5-letter words. So if you can just do some simple combinatorics in your head, yeah, it's a pretty, because you're looking at not only the 12,000 8-letter words on each row, but you've got to check that all the different pieces are starts of 5-letter words. So you've got a lot of basically comparing to do, a lot of searching to do. So then what? Well, this is actually the first puzzle I wrote for the Puzzle Cabaret, and it took me, it took me at least a week, I think, to kind of finally go through it. And I had to learn a bit along the way. What I found is this command called word frequency data, which gives you the frequency of a word in typical English text. And it uses millions of Google books, and it uses data sets called n-grams, which are the number of times letters of a certain sequence will occur in a book. And what I thought, well, I don't need words like urticaria, right? So what I did is I looked at all the 8-letter words and I picked the 6,000 most common of those and 3,000 most common 5-letter words relative to the Google book database. And this took a couple of hours because there's a lot of searching to do. But for those of you who know something about programming, this is something called pre-processing, meaning that once you do it, it's done. You don't have to do it every time. So what I do is, maybe I work on the layout for another puzzle while the Mathematica program is running and doing all this searching. So once that was done, then it actually turns out that it worked. And I'm just going to show you a typical output. So the first word is cassette, and rest conditions, we don't need to really know what that is. And it takes a while usually to get started, but then it will spit out the grid. You can see cassettes, leathers, requests, and then the 5 and 4-letter words are in a list that follows. And you curate. Now this again, I wouldn't want to use this. I've got too many plurals. I feel like that's a little cheating if you've got 8-letter words and they're all 7-letter words, which are plurals. So leathers, requests, caresses, archives, and you also have then tests, eyes, cares. Not so bad there. I think the 5 and the 4-letter words are okay, but again, I try to avoid too many plurals. And since you've got Mathematica and it just keeps spitting things out at you, you can sometimes be pretty picky. Sometimes the cassette, the first word, you don't get anything, and so but often enough, it doesn't happen all the time. You pick a word you start with a word that has common letters. You don't start with a word like jonquils that has a J and a Q, for example. You start with a word that is more accessible. And then again, you curate, and then you go back and you write clues. So this really is something I could not have done without using Mathematica. So this was an example of a complex search. The next example is what I call an iterative search or interactive. This is a puzzle I call word Tetris. What you do is you drop these Tetris pieces into the grid, and you make 7-letter words reading across. The clues are not in order. And when you drop them, they can pass through the TETRIS squares. So those are not actually obstacles. Now, what makes this, I think, an interesting puzzle is if you look at this IISS tetramino in the upper left, you can rotate that 180 degrees. If you look at the OOSI in the bottom right, you can rotate that 180 degrees. So things that have HINOSXZ, you can rotate pieces like that. And so what I wanted to do is have several pieces have those letters in them. So we start with a grid and divide it into tetraminos, that's really easy to do. It's much easier than pentamino, since we do have to repeat. And so I wanted 10 of these pieces to be rotatable. Then when I say I'm doing this interactively, as we're going to see in the next slide, to package it all together sometimes takes a lot of work to embed things in this complete procedure. So if the interactive process is fairly efficient, I just stick with it. And so let me say now just what that means. So my find command, now I'm going to go back and forth for a second, but the --XXXT means if you look at that top row, the first 3 letters can be anything. And then the next 3, the XXX, are ones I want to be rotatable. And then I've got a T in because I've got the T from Tetris. And if you look at number 2, find dash X's dash, on line 2, the first and last letters can be anything, but the middle 5 letters have to be rotatable. And then you curate. And there's a lot of nice words here. Usually if you start with Tetris and since you have the letters HIONS, you're usually going to find several options that you can use in this, and then you just go one line at a time. But again, you don't have to sit there trying to wonder. You can just use Mathematica, and within 10 or 15 minutes, you've got the puzzle done, and then you can go work on the clues. But again, pretty tricky to. I think this would be easier to do than some of the others without Mathematica, but still, it's it really does help quite a bit. So that's called so I'm calling an interactive search. Uniqueness, that's another important thing. This is called same sum. And if you take a look at it in the upper right, you see this is a puzzle where you circle a bunch of letters and circle a bunch of numbers so that they add up to the same thing in every row and every column. And ridiculously simple to create a puzzle, not so simple to show you've got a unique solution. So those are two examples from the book. And it's nothing more than exhaustive search because the numbers you only have a range of things they can add up to. For example, the first puzzle, the first line adds up to 42, and then what's going to be the smallest one, maybe line 4 is going to be 31. And then you can look at which things add up. The search space is not that large, so it's easy to find if you've got a unique puzzle. As I mentioned before, really you do want the puzzle solutions to be unique. I think that's the mark of a good puzzle creator, or one mark of a good puzzle creator. You want your solutions to be unique. Okay, now here's an example of a puzzle called Squares, which I've got a friend helping me to work on finding uniqueness here. I haven't really tackled the uniqueness with Mathematica, but I'm going to show you some issues here why. But first, I just want to take a minute to explain what this puzzle is. And so if you take a look at the grid on the left, you see numbers at the end of columns or rows and columns. And that indicates how many gray squares you want to fill in. 4 in the first row, 2 in the second, etc. And when you fill in, you want to make squares of sizes 2, 2, 3, and 4. So if you look at the grid on the right, you'll see that the 4 gray squares labeled A make a 2 by 2 square. The 4 gray squares labeled B make a 2 by 2 square. The 4 labeled C make a 3 by 3 square. And the 4 labeled 4 are the corners of a 4 by 4 square. So you fill in such that every gray square is a part of some square. You can't just have random gray squares that are not affiliated with one of the larger squares. And so your goal is to fill in the grid in such a way that you get the correct sizes of squares. Now that's just a simple example. This is an example of something which is a bit larger, where you've got squares of sizes 2, 2, 3, 4, 6, and 6. And I want to talk here about the search space. So let's just for a moment take a look of a 2 by 2 square. Where can the upper left-hand corner of a 2 by 2 square be? Well, anywhere except the last row or column, right? For the upper left-hand corner. For a 4 by 4 square, well, you can't be in the last 3 rows or 3 columns for your upper left-hand corner. So you've got 5 squared, which is 25 options for the 4 by 4 squares. So when you take a look at this puzzle and you look at your search space for finding all upper left-hand corners of the 2, 2, 3, 4, 6, 6, of course, it's really 49 and 48, right? Because they're not going to be in the same place. But just for a back of the envelope calculation, we get 175 million things to check. And every time you check, you've also got to do all this work to make sure the correct number of squares are filled in, that there's not too many squares in a row or column. And I've tried some attempts. I just haven't been able to wrap my head around it. But one of my good friends in Illinois has a student in a programming class, and he's interested in maybe trying to write something in C++. And for those of you knowing something about that, C++ is usually, things can happen much, much more quickly in C++ because it's a compiled language. You can compile Mathematica, but you're still having the restrictions of this particular programming language. So I think I'm going to try to write a brute force one, but I'm not really hopeful that it'll work for the smaller puzzles. But when you start to get 8 and 9 and 10 size grids, the search space is going to be just phenomenal. So yes, I have to check uniqueness by hand for these, and can sometimes take half an hour or an hour just to show that some solution is unique. Now something kind of a little bit different. I use it also for layout, and this isn't so much necessary, but it makes things a little easier. So if you've looked at puzzle books, you see these puzzles where you have to drop the letters down and make a quote, right? Well, my spin on this is some of the letters are wrong. And when you fix the letters, you can anagram them to make an answer to the clue, which is the state where Katherine Johnson grew up, and the quote is by Katherine Johnson. Now, if you do any layout of any sort, you know that trying to put all those letters in all the right places and having, it's very, very, very tedious. So what I did is wrote a little routine which does it for me. Again, I use Tixi within LaTeX, as I mentioned before. So I just have a function which spits out all those lines of Tixi code, which I can just cut and paste into my LaTeX document. And, for a number of puzzles, I do things like this. It just makes the layout easy. And again, once you do it once, writing these misquotes puzzles now is really a pretty quick thing. You just have to find a nice quote, find a clue and switch out some of the letters. But the hardest part then putting it together is the layout, and you just write some routines that do the layout for you. So again, just to summarize, we had started with simple searches, we had complex searches, simple predicates, complex predicates, we had interactive searches, we wanted to show uniqueness, and we've got layout. All I want to say is have fun with ideas like this if you want. I love creating puzzles, and I really like how Mathematica is a tool that I can use to create puzzles I could not have attempted to do by hand. And some of them, like the squares puzzles I showed you, I do by hand. But the word puzzles, I would say, 90% of them I use Mathematica in some way. And again, that's the reason why I can put together these volumes of books, because I have that Mathematica to do the heavy lifting. Just a quick comment that there's a second section of logic and math puzzles, like the same sum that I showed you earlier. And logic puzzles, I just brute force them. I don't have any way to use Mathematica to do logic puzzles, but if you're like me, you still love making logic puzzles anyways. So there's my email. Please email me with questions, ideas, collaborative ideas. Got a website, I've got a blog. So that's what I have to say.